All right, so Julia, where are you running off to? Go, 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 go. We'll wait for Julia. We'll wait. So we're coming to the end of lectures. In the schedule, I have a lecture for Monday, which is the wrap up. We can still do something on Friday, or we can make it we could make it a party. Yeah, we can make it a party, or we could have a party in the lab where we just kind of help out with project stuff. Does that sound like a better plan than doing a lecture next Friday? I'll just be there in the lab the whole time, and we'll go with that. Okay, I think that makes the most sense. Yeah, sure do whatever you want. We can make it into a party. We will have snacks for the final project day. We'll probably have something, raspberry pies or something. I don't know, something.
That's so cute.
I don't know. Raspberry pies maybe raspberry cupcakes or something. I don't know. I don't know if raspberry pies are very good. But anyway, so final lecture will be on Monday. We'll do a kind of a wrap up about what we all talked about. And then I promise we wait for Julia, so I won't quite start this stuff yet. Any questions on the project or otherwise? Yes?
Do we have a lab next week then?
There is a lab next week. It's just project. So, I mean, just come. We'll talk about project, help you work on things. And obviously, it's best if you can come with your partner, but or if your team. And either day is fine. That's fine. Okay. Other questions? No? Oh, hi. Welcome back. All we talked about so far was that next Friday will be we won't have a lecture, we'll be in lab. If you want. You don't. It's optional, but that's what we do. All right. Anything else? Okay. So it turns out that in the spring quarter, when this class has been normally taught or has been taught every other time, there are 1 or 2 lectures that are fewer than this quarter. I don't know if you guys know that. There's because of holidays and things. So we kind of finished everything up. And then today I thought, well, over the last few days, I thought, what am I going to do on Friday? Or today. And I said, one of the things we haven't talked about, which they do in CS 107, and I think it's kind of a cool topic, is floating point numbers. And one of the reasons I thought we'd do this is I've gotten a few questions about this. Andrea emailed and said, hey, can we use the sine and cosine libraries and things? And the answer is yes. It's in the math library, and I can put a little guide up or just show you how to do that. So it's pretty straightforward. And then somebody else asked about, can we just use floating point numbers in general? And the answer is yes, sure. You can use floating point numbers. The Pi certainly understands them, and they are just basically decimal numbers, etc. Well, we'll talk about specifics about what they are. Tom, you had a question.
Well, I looked for a math library and I didn't find one.
Yeah, so I tell you what, if you remind me right after class, I'll put something on Piazza about how to do it. It's easy. It's very easy to do. It's the -LM library, and you have to include math.h. Otherwise, not too hard. That reminds me, since I'm speaking to Tom, who's using the I²C libraries? A few of you, right? Tom found a bug in the I²C library and did some heroic work to get a logic analyzer hooked up and figured out that there was a bug, so we fixed it, hopefully. We're still trying to figure out if there's other issues, but anyway, thank you, Tom, so that's better. And then hopefully you saw the Piazza post where I put up some information about the other things like the website, getting to a website, or hosting a website on an ESP32 Arduino, and then the communications and so forth. So I put a few more guides up there, and also about the SD card library. So things are getting fleshed out. If you want to use some of those other things that we talked about, you can do that. And just let me know if you have any particular questions about those. Okay, anything else? Yeah, Arjun.
So when if we're using multiple I2C devices, just because the way that we write the libraries or whatever, a lot of the function names will be similar. Or you might have a begin function for two
Sure.
different devices, and in Arduino and stuff we have different namespaces that we can create.
Mm-hmm.
Can we do that in C, or should we just have different function names?
Yeah, it's a good question. In C, there are no namespaces, so everything's one global namespace, which means you should just have a preface to all your functions for that particular thing. It shouldn't be too hard to make those changes. But yes. Now, I thought you were going to ask how do you use multiple I²C devices at the same time? If they have different ID numbers, and if you're using 2 different sensors, they generally will. But in the case of this team, they want to use 3 of the same sensor, and there's only 2 different IDs. So it's like, what do? There's a thing called a multiplexer, which allows you to select which device is actually listening. I have a few multiplexer chips. I got to get you the one you wanted, and it's possible to do. So there are many ways to do that and to get it to work. All right. Any other questions? Okay. Let's talk about floating point numbers. Okay. Now, floating point numbers are numbers that are not integers, and we'll get into some of the details about that. This little comic, I think, is relatively funny if you get what's going on, and we will by the end of class. But basically, it says there's a robot sitting here, and it says, "Welcome to the secret robot internet," and there's a CAPTCHA, and it says, "Prove you are human," and it says 0 plus 0.1 plus 0.2, and it says 0.30004, and then he got into the internet. So if you don't understand this joke yet, you will at the end of the class, and I think it's interesting why this joke is actually a thing. So let's talk about numbers. Logistics, next week's lab, as I said, we're discussing projects. Final presentations, the last day of finals, which is probably good because you have more time. Not good if you wanted to get out of town early, but sorry. And then we'll do all this stuff on cool floating point values. There's this format that we're going to talk about called the IEEE 754 floating point format. And it's the way most computers these days do floating point, the numbers we're going to talk about. And it's a standard. It's not like this was like defined on high by some like mathematical nature or something like that. There's a format of how we do these numbers that some smart people had to think about, and that's what we're going to get into the details of. Okay, numbers. Real numbers is what we're talking about now, right? Like 1/5. Right? We're talking about numbers like 1/5, right, which is just 0.2. We haven't dealt with numbers like that in the low level. I mean, you might have used doubles or floats in 106A or 106B, but now we're going to get into like the nitty-gritty how these things actually work. Here's another one. 1/3 is a little different than 1/5, right? Why is 1/3 different? It's repeating, right? It's got this interesting like feature to it where you got like that. When I was in 6th grade and I learned about this was like mind-blowing. Like, oh my gosh, repeating, what does that mean? It goes on forever. How is that a thing? I don't get it, whatever. But that's kind of a thing, and it's pretty cool, right? The like repeating part itself was interesting. And of course, we've got other interesting real numbers too, like irrational numbers that repeat, that continue to infinity but don't repeat, and those are weird too. So we have to think about how our computer is going to represent these sorts of things. Okay? You might think, by the way, that 1/3 you could have a rational class to do that. But then, what if you get into irrational numbers? Then all bets are off, right? So things get a little bit strange. Okay? You've seen numbers in the Raspberry Pi that are integers. Once you get into real numbers, things get tricky. It's not just this like simple, like we just go and do it this way. It gets a little bit tricky, okay? So as I said, you can represent some rational numbers exactly, okay? Now, by the way, that's in base 10. I'll explain why that's important in a few minutes. You can represent some rational numbers, not exactly, but we have like indefinitely repeating. And then irrational numbers have you can't represent irrational numbers by a fixed number of decimal digits either. It's just impossible, right? So the question is, how do we do this in the computer? And that's where it starts to get interesting. Okay, that's where it starts to get interesting. All right, we have choices. Okay, like lots of other things, we have some choices. Here's some constraints that I'm going to impose upon this. And you don't have to have these constraints, but let's go through the ones that I think are important here. We want to represent real numbers in a fixed number of bits. You don't have to do that. There are libraries that allow you to have more bits. But let's say that we want to do this. How many bits do we have in an int? 32. Let's write a format that will allow us to use 32 bits to represent the numbers we want. That's what we're trying to do there. Okay? What that means is that you're not going to be able to represent all real numbers. How many real numbers are there? An infinity number of real numbers, right? We also can't represent all integers in a fixed number of bits because you only have a certain number of bits. But what's more interesting is that the way the numbers you choose to represent is kind of important. Okay? You can't represent all rational numbers in a range either. Like even in a range, between 0 and 10, how many rational numbers are there? Infinite, right? Because you can prove that, right? Go into a math class and you can prove that, right? But the point is we're going to have to make some choices about which numbers we actually represent. That's interesting too. Okay, we want to represent a large range of numbers. That's an important one. We want to be able to say, represent really small numbers. Let's say we're biologists working at some sort of nanoscale or whatever, or atomic scale or something like that. We also want to represent giant numbers if we're astronomers and whatever. We want our number system to be able to give tiny little numbers and giant numbers. Okay, it'd be helpful if we could do negative ones too. Should say that. We also want to be able to perform calculations. It'd be kind of dumb if we had a system where we're like, oh, here's a big number, but we can't do anything with them. You can just look at them, right? We want to be able to make it so that we can do the calculations. Okay, you get those constraints? All right. Here's an idea. One way to do this is fixed point arithmetic, or fixed point numbers, okay? We already have been using fixed point numbers. Integers are have an implicit decimal place, or binary point, as they say, at the end of the number before it goes into the decimal range, right? Or all the numbers after the point, okay? 1234 is really just 1,234.0000 with all zeros there. We're just saying we're fixing the decimal point there, and then all the numbers are there. Does that make sense? That's what we're doing with integers, basically. Well, you don't have to do that just with integers. You could do that you could say, let's have the decimal place here in our number so that we always have two numbers after it that are after the decimal place. Okay? This is what it would look like if you were doing one digit each time. Some digit D2, D1, D0, and then D negative 1, D negative 2. These 2's are the powers of 10 if we're talking about decimal numbers, right? The 1 is 1 times 10 to the second, 1 times 10 to the first, 1 times 10 to the 0. 1 times 10 to the what? Negative 1, 1 times 10 to the negative 2. That's how that number gets represented. But if we do a fixed point, we can represent some of these numbers we've been talking about, right? What you can do is you can say, now you can represent, if we did this, if we had the point there, what range of numbers can we represent? Forget the negative ones, just the positive ones. What numbers can we represent here? If we have that many digits only, and we put the decimal place right there. Let's say you start at 0. What's the biggest number I could represent here? 999.99, right? So you could represent those numbers using this fixed point. We have 5 digits now, but we can only represent 300 places. But this is one way to think about it. We could do that, right? What's the precision that we have? And this is an important one. How much precision do we have? In other words, how precise a number can we get? Hundredths place, sure, right? You can represent the hundredths place, 5 decimal digits of precision with hundredths place. Great, right? There are some numbers we can't represent, right? There are even some rational ones. 123.456 can't do it. We don't have, remember, we only have 2 after that decimal place. We can't do that number. Not going to happen, okay? 1, 2, 3, but 3, same thing with the repeating. It's not going to happen. 1,000, nope, we can't represent 1,000. We already said 999.99 is biggest. 0.001, you can't do that, too many decimal places. We might call that something called underflow, right? So you do have to do some rounding or truncating, and that's important, all right? But fixed point arithmetic's really easy, right? You know where the decimal place is, and you do the math, and it's really easy. You just line up the decimal places. If you're doing addition, add. If you're doing multiplication, you do the line up the decimal places, do the multiplication like you normally would, and then round it maybe at the end. Pretty simple though. So it's not a bad way to do this. What is one of the problems with this? Right? It's kind of limiting, right? We can do regular arithmetic, but the range is pretty limited, right? Wherever you fix that decimal place, you've now got a range that's pretty tiny. If we put the decimal place before the, or I guess before, like we made the decimal place there and said these are our numbers, you can't represent any number bigger than 1. You can't even represent 1. They all have to be less than 1, right? And you can only get that range. So the range is limiting. So this has some limitations, although it's not terrible. Okay? It has some good features too, but not terrible. Okay? Here's another idea. We can represent numbers, and this is now called floating point. In other words, the decimal place floats around the number, and you don't fix it in one particular place. We can represent numbers in this form. Okay? V equals x times 2 to the y. Okay? And for various values of x and y. Okay? Meaning that we're going to give some number here, and then also some power of 2 in a different part of our bits that says this form, that gives this form. Okay? Let's look at the, and by the way, we're going to call these 3 parts. There's going to be 3 parts really. A sign bit, which will tell us whether or not it's positive or negative. An exponent, which is that y, and a fractional value. Okay? All right. And we kind of already talked about this, right? That these are the negative powers of 2 for after the decimal place, or negative powers of 10 after the decimal place. If it's binary, powers of 2, right? So binary numbers, and you may never in your life have seen a number like 101.11101 in binary. You can do binary with a binary point, why not? It just means that this is 1 times 2 to the what? 2, 1 times 2 to the 1, 1 times 2 to the 0, 1 times 2 to the negative 1, which is 1/2, 1 times 2 to the negative 2, which is 1/4, 1 times 2 to the negative 3, which is 1/8. Yeah, it starts getting a little weird, right? Okay. There's a converter that I wrote, a little JavaScript program that you can look at if you want. I'll just go there really quickly. It will allow you to do some conversions. Let me bring this up here. Make it a little bit bigger. It'll allow you to do some conversions. So if we type 10.110 like that, right? That's 2.75. And if you go down here and you say 2.75, you can convert that to 10.11, right? Is that what I typed up there? Yeah, 110, right. So that's that. So you can do this conversion in here. It's a little converter. We'll get back to this in a little bit. Okay? But you get the idea of how binary values are going to work. Powers of 2. Negative powers are 2, 1/2, 1/4, 1/8, 1/16, etc. Okay. All right. Here is an example, right? 101.11. You just do exactly the same thing you normally do, and it ends up being 5 3/4 or 5.75. 101.11. 101.11. 5.75. Okay? And the 5 part we already know. 101, that's easy. We would recognize that as 5. But the 0.11, you got to do a little bit of, it's 1/4 plus 1/2. Right? Or I guess 1/2 plus 1/4. Everybody with me so far? All right. What happens if you shift the binary point to the left by 1? 101.11, if I shifted it to the left by 1, what would happen to that number? Skylar? It's going to divide it by 2. Right? Just like any other time if we shift by 1. Remember how we shift? That's one of the ways of like shifting by 1, we divide the number by 2, or if we shift the other way, what happens? Multiply by 2, right? Same thing. If we did this, so 5.75 times 2 is what? 5.75 times 2 is 11.5, right? So would that make sense? 1011.1. 1011.1, right? There's 11, and 0.1 is half, 1/2. Oh, it works. Very good. Okay? If you want, you can also, there's this thing called epsilon, which is basically saying if you have 0.111 all the way to the end, you're 1 fewer than the smallest. That's actually the smallest like fraction you can do, or not the smallest, but the biggest fraction less than 1 that you can do. All 0.1s. Just like 0.99999 is a little less than 1. It's the same thing here. Scott, did you have a question?
No, I'm just stretching.
Oh, you're just stretching. Okay. All right. Fractional numbers in decimal, some of them you can't represent exactly, right? 1/3 and 1/5 you can't. In binary, you can't represent 1/3 or 1/5. You can't even represent 1/10 in binary exactly. What's that mean? Let's take a look at this little program here. Okay, I'll actually run it for you. We've got a buffer here. There is no printf in the real world has the ability to print out floating point numbers, but I had to go find a library to do a conversion, and I couldn't work it into printf right now. But there's a conversion called FTOA, floating point to ASCII, which basically converts to a string that you can use. But if we do this, if we say float f equals 0.1, right? And we do the, let's see, oops, let's actually, there we go. I will go look at this. FTOA. Nope, wrong one. Floating point. Okay. Oops, this is a different number. Hang on. Maybe I didn't have this one in here. Test 10th. There we go. Test 10th. All right. Here's our program. This is the same exact program here. Let's see what happens when we run it. Okay, it's basically going to create a buffer, create a floating point number of 0.1, and then convert it to decimal, or convert it to a string and print it out. Make install. Okay, there we go. And look at that. 0.1 in binary converts into, or if you try to do 0.1 in decimal, right, this is what it's actually, how it's actually represented in the computer. You can't represent it exactly. 0.1. This is one of the reasons that, like, you can't really use floating point numbers for currency, because you've got issues with that. Okay, we'll talk about a little more detail about why this is the case a little later. But the big point, and this, by the way, helps solve the riddle of that joke at the beginning of the thing, right? 0.3 is not what you think it is necessarily. Okay, so if we run this, we get that. Turns out that unless your numbers can be exactly written in this form, x and 2 to the y, you won't be able to actually represent it in a certain fixed number of bits. Okay? Interesting, huh? Okay. Actually, let's go check, by the way, while I'm thinking about it, let's check here. If we do, oops, if we do 0.1 convert, there we go. That's it, right? And it's a repeating decimal, as it turns out. 0.1 is it's a rational number, so it has to be a repeating decimal. Looks what it is. 00011 0011 0011 0011 in binary. And I made this so that you could do it as many decimal places as you wanted. So let's say we had 400 decimal places and tried to convert that number. Well, just keeps on going. It's a repeating decimal or a repeating binary fraction, turns out. Okay, so we got to worry about that in our little format here. Okay? IEEE format that I mentioned earlier had to make choices. Now, this is a really terrible day to be mentioning this, but the guy who kind of originally invented this was a professor at Berkeley. Sorry. So bad timing. But I know. But anyway, he happened to be really smart. And by the way, smart people work at lots of universities, including Berkeley. So we try to get him down here. But anyway, what he did was he thought about this, and he used those constraints we had earlier. And he said, let's see if we can come up with a standard that will be able to be used on all computers. And this is nice, because if you don't have a standard, then numbers end up different on different computers, and you kind of don't want that. You at least want them to behave the same on all computers, right? Even though there might be quirks still, you want them to behave the same. So this is what he came up with. He said, and the standard that the team that ended up finalizing came up with is this. This is what we saw earlier a little bit. We're going to create a number, -1 to the sign bit. All right, what's -1 to the 0? 1, right? Because anything raised, so that's 0. And -1 to the 1 is -1. So if you have a bit that's the sign bit, if it's a 0, it means it's a positive number. If it's a 1, it's a negative number. We've seen that before anyway, which is nice. Then you have this other thing. It's called M up here. I like to call it the significand. It's also called a mantissa, and that's kind of from logarithms. But it's not logarithms, so it's a weird name for it. But anyway, I like calling it the significand, which is how significant, like the significant parts of the number. And then we also have, and it's a fraction, by the way. We'll get to the details of that in a minute. And then there's an exponent, and the exponent weights the value by some amount. Okay? This is the form we're going to use to do these numbers. Okay. Here's an example. If we have a sign bit of 0, we have a mantissa or a significand of 1.5, and an exponent of 9. You just do this calculation, and that's 768. Okay, so that's what we could do, 768. Remember, it's 2 raised to the 9th power in this case. So it's that's the way it works. Okay. All right. To do this in our bits, remember, we only have a certain number of bits. We can do either 64 or 32. Let's stick with the 32 right now. Here's what it looks like. And somebody had to decide these numbers. These are not like, oh, this is the way it is. Somebody had to decide this. They said 1 bit for a sign. That was pretty easy. And then they said, oh, let's do this. Let's make this a 7-bit exponent. 23, 24, 25, 26, 27, 28, 29, 30. Sorry, 8-bit exponent. And the rest of the 23 bits will be the fractional part. This is what it looks like in your number. Okay? All right. Now, before we continue, some of you are saying to yourself, well, I'm checked out. Some of you are saying, this is kind of complicated, isn't it? You've got these 32 bits, and you've got placing things in there, and there's raising to the 2 and all this. Yes. All right? This stuff is complicated. But I want you to appreciate some things about it. Here's what I want you to appreciate. First of all, it was based on decisions and choices, right, with good reason. This stuff might be complicated, but it's not like they just said, oh, let's make it complicated. They said, we're doing this for a very specific reason, and we'll talk about why. Okay? Secondly, it's efficient. Computers, if nothing else, need to be efficient because you're trying to solve big problems. They need to be fast and whatever, right? They tried to make this a really efficient system, the way the bits are laid out and everything. And it was just choice. It was a choice. But they made the choice because they thought about it and went, oh, what's going to be most efficient? Let's do it this way, right? I don't want you to think, this is way too hard. I could never come up with this myself. Look, I couldn't come up with this myself, right? Maybe if I was on a team where I've been thinking about numbers for like years and years, and then I'd be able to, whatever, right? I would rather you just appreciate the fact that, hey, this is a kind of a cool way of representing numbers. Might not be the only way, right? On some other planet, some other species might be deciding some other, way of doing it, but this is a pretty good one, as it turns out. Okay? All right. Now, here's some more technical details. You ready for this? A floating point number can be normalized. We will get to denormalized, ones that aren't normalized, if the exponent is not all zeros or not all ones. In other words, you look at the bits in the exponent, and if it's all zeros and all ones, you can't do what I'm about to do. We'll talk about that in a minute, about why that's the case. Okay? It's the most common thing. Most numbers don't have all zeros or all ones in the exponent. Okay? The exponent itself is a signed integer. Wouldn't it be nice to be able to, we're going to try to do giant numbers or tiny numbers, so we want the exponent to have negative and positive values itself. Right? It's not a bad idea. Having the exponent should be able to be negative or positive. It's in this weird form called biased form, which means that the actual number in the exponent has been added to, 127 has been added to it. So the number you read up in the exponent, it's going to be off by 127. Well, how do you get it back? The actual exponent, you subtract 127. Here's the reason that you might go, well, why would they do that? What's the point of doing that? The point is so that you can compare numbers. Okay, so what they do is it's not a 2's complement number anymore. There are no 2's complements. That's behind us now. It's just a set of bits that are from small to big, but the smallest ones are the negatives and the bigger ones are the positive ones, and they've got the middle there. So what they do is they just say, fine, we're just going to offset it so that you can compare this very easily. That's it. No 2's complement. That's why they do that. Here's the next cool, this is the thing I'm about to talk about, is the coolest thing about this entire system. The fraction part is represented as a number between 0 and 1, okay? And it has what we call an implied leading 1. Now, if I have a number between 0 and 1, or I should say, if I know that this fraction is between 0 and 1, okay, then I can actually get an entire bit, which doesn't sound like much, but for every number that sounds, an entire bit or digit for free. Okay? And I'll show you what that means. But the bottom line is that if you look at this fraction, you add 1 to it to do it. So it's just a number, and it starts at like 0.0. So if the number up here was 1, whoops, if it was 1 0 1 1 1 0 whatever, This means, in binary, 0.10110 with a 1 like that. It means 1.110, da da da. Okay? All right. Basically what it means is, if all numbers are between 1 and 2 with that extra 1 in there, you don't need that first 1. We'll look at a little more detail in a second. Okay? All right. This is the precision part for free. Okay? If you know that the number is always between 1 and 2, what's the first digit always going to be? 1. Why represent that 1 in our number itself if we know it's always going to be there? Just represent everything but that 1, and you know that that 1 is always going to be there. So you get the extra bit at the end for free, in other words. It's instead of saying, oh, why instead of putting the 1 there, we want this number to always be between 1 and 2. Well, fine, let's just make it between 0 and 1 and assume that that 1 is already there. We get an extra bit for free. It's a cool, like you gotta, and the first time you hear it, you go, I don't know what you're talking about. But if you think about it, you go, oh, that's actually pretty neat. That you actually can get an extra bit of information out of this by ignoring the fact that it's always that big. Yes?
So why did we add, so why, originally we were bounding f by 0 and 1.
Yeah. So let's look at the format for a second here, right? Okay. This number here is what we're going to multiply by 2 to the e. Okay. We have to pick some range for it. We're going to end up picking the range between 1 and 2 for that number. Okay. And then you always pick the exponent to based on where you want the number to actually be, right? If we didn't fix that number in a particular place, then there wouldn't be a unique numbering anyway, and it'd be a little weird. Now this is going to allow for a unique numbering, and it's going to allow you to, well, as I said, get that extra bit for free because you know that it's between 1 and 2, therefore the 1 is not necessary. You get that extra 1 here. So where was it here? Right? Yeah, there we go, like this. Okay? And let's look at this example. When you sometimes need an example to actually do this. Here's an example of a floating point number. Yeah, sorry.
My question, so like why did they choose 1 and 2? Why didn't they just make m between 0 and 1?
Yeah, this is a good question. Well, first of all, how would you end up representing 0 itself? That's one of the problems. Okay, there's an issue with that. But let's see how this may kind of help us to frame why they did it if we look at this example. Okay, here's a 32-bit number. Okay, we said this. We've got the sign, we've got the exponent, and we've got the significand over there. Okay, the sign is going to be positive. We know that. Okay, because it's 0. The exponent is going to be 0.1111110, which is here. But we said that it had been added to 127 had been added to that. So that's 126 as it turns out. So 126 minus 127 gives you -1. So that's what the exponent is that we're going to do. Everybody with me there? Okay. Then you look at this number and you say, okay, great. Zeros are all zeros, but we said we add 1 to that if this is 0.0000. Okay? So what we're going to multiply now by is not 0, but it's 1. Right? So we're going to end up with our 1 times 2 to the -1, which is from our exponent, plus the sign to the sign bit, which is 1/2. This is how you represent 0.5 in this format. Okay? This is how you represent 0.5 in this format. And again, if we tried to do it between 0 and 1, this little 0, we wouldn't have that, we would have an extra, like we wouldn't be able to use that extra 0, in other words. We know that it's 1 in there, so we get the extra bit at the end. Anyway, this is the format. Okay, this is how it ends up coming out. Okay, there's another converter, aside from the one I showed you earlier, that is, let's see if I can get, there we go, that looks like this. And we said that the number was, let's just type in 0.5 in here. Let me make this bigger. Okay, if you type in 0.5, right, it actually fills in the details here. And I made it too big. There we go. One more. There we go. Okay, it fills in the details there. 0, 0, the checks are all 1s, and da-da-da-da-da. Okay? All right. If I wanted to shift this number by some power of 2. I could just continue adding or subtracting more. That's not going to work because that's all 1s, but there you go. These numbers are all powers of 2, as it turns out. These are all powers of 2 that these numbers are representing. Okay. If you didn't quite get all that math, that's okay. There's lots of other examples you can do. Okay, here's another example right here. Let's look at this number. All right. What's the sign going to be for this number? Positive. Okay. This number, 100000100. Well, let's figure out what that is. Okay, we can go to the converter if we want and do this. You don't have to, probably not going to do this like in your head, right? In this case, 1 with 4 zeros, 100. 1 with 4 zeros, 100. Convert 132. So that number is 132, meaning that our actual exponent is going to be what? 132 minus 127 gives us an exponent of 5. So we're going to end up multiplying by 2 to the 5th. Okay, let's look at this one. 0101 with 000. Well, you can actually do this. This is 1/4 plus 1/16. 1/2, quarter, 1/8, 16th. That's what that is. 1/4 plus 1/16. But let's just type it into the thing. It's 0. It's 0.0101. Almost. What do we say we always add to here? A 1. It's actually 1.0101. So let's see. Oops, wrong one. 1.0101. Convert that, we get 1.3125. That's what this number in binary is. Okay, 1.3125. So in here, it's going to be 1.3125 times 2 to the 5th. 2 to the 5th is 32. So let's see if this works. Whoops, let's do this. 1.3125 times 32 is 42. That's what this number should be. And there it is, 42, which is, yeah, there we go, 42. Right, here. Question, Tom.
So, if doubles are represented by v equals x times 2 to the y, and n is a double, why can't we just group the 2 to the y plus e?
Hold on, so it's not m as a double. It's that there's, in this case, 32 bits, which by the way is float, not double. That's okay. Let's pretend there's 32 bits here, right? You've only got these 32 bits to work with. We just pick each part and say we're going to have an exponent part and a decimal part, or a binary part, and that's how we're going to, and then that format will allow us to get the range. Why is this a big range now? That exponent can go from negative 126 all the way up to 127. Or maybe it's the other way around, negative 127 to 126. But anyway, it's big. That range means we can do numbers up between 2 to the negative 127 all the way up to 2 to the 126. That's a lot of range. That's where the range comes from. And then this gives you a pretty good precision, it turns out. Did that answer your question? Or that probably didn't answer your question, but I mean, they didn't get your question.
I was thinking, well, you showed us the 2 equations.
Yep.
For double and float. I was just thinking, why don't they?
Did I show you 2 for double and float?
Just 1 for each. But
Which one was this? Go back, tell me. Stop me on the slide where that. Is that it?
Yeah. Well, so if you take the equation for double,
This is the equation for both.
For both.
Yeah.
Oh.
This is the equation for both, but it's just different number of bits. 64 bits are doubles. Floats are 32 bits.
Okay.
That's the difference. It's just a different number of. Here. You've always got one sign bit. For floats, you happen to have 8 exponent bits, and then you have the rest 23 fraction bits. It's more for the other. It's like 11 and then 53 or something like that.
What was the purpose of the v equals x times 2 to the y?
Oh, that was just saying those are the only ones you can represent exactly.
Oh.
Those are only numbers you can represent exactly. If you have that in a form, that's the only ones you can represent exactly.
Sorry.
Right. No, that's right. Okay. All right. So where were we here? We did that example. Here's another example. Let's see. Here's another example. Like, let's see. That's the 42 one. Okay. And you can try some more. We don't need to go through all these, but if you want to try them, you can. And it's just the same like rote way of doing the actual conversion. If you want to convert the other way, you have to do a little bit of other things. Yeah, Julia.
I was wondering why it can't be all zeros or all ones.
We will get to why it can't be zeros and all ones. The part of the reason is that, you mean the exponent? Well, you've got other certain numbers that you want to talk about. We'll get there. Don't stress too much about that. Okay. All right. So you could convert some more. Okay. Here's another one. All right. You convert some more. Okay. All right. Let's take a little break. 3 minutes break. Okay. I always did this in 107. I haven't done this in this class. I think for whatever reason we're a smaller group and whatever. Sometimes you need a break when your brain is like, take 3 minutes and take a break. And then we'll come back and do some more. And I'm happy to answer questions.
Are we going to cover how to represent zero? Just the numbers?
We are going to talk that you can't represent 0 in this method because it's a number between 1 and 2. So you can't do that yet, but we will get there. Yeah. Yeah.
So I'm still confused about why you bias if I
Right.
7.
That's a good question. Here's what's going on with that. So the exponent has 8 bits, right? We said it can't be all zeros and can't be all ones. So the smallest number that it could be is 0.00001. Okay? We want what's that number in binary? What's 0.001? 1. So if we subtract 127, what does that mean that the exponent's going to be? Negative 126, right? You could have 1, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7. The biggest number you can have is 1, 2, 3, 4, 5, 6, 7, 0, because you can't have all ones. That's another special thing, right? What's this number going to be? Well, let's think about this. The number, it's going to be 2 less than 2 to the 9th, basically, or 2 to the 8. Sorry, 2 less than 256. So 254 is the biggest one here. This is 254. Okay, 254 minus 127 is what?
It's
127. That's the biggest exponent. Okay. Now, now this is your range between here and here, right? If you want to compare two numbers, right? These are going to be small and these are going to be large. All you need to do is compare the exponents and you can say whether one number is bigger or smaller than the other. That's the reason they do it.
And if the exponents are the same, then you go down to
You'd have to go down to the, you'd have to go to the,
Just a hypothetical.
yeah.
With that system, we can store from negative 127 to
Negative 126, yeah.
to 126.
You could basically 2 to the negative 126 times 1.1111 in binary. So yes, basically, yeah.
So with that system, we can store that range.
Uh-huh.
What if we got rid of one of the bits in that 8-bit signature and use one of them as a way to, like another sign bit for the exponent, and then we had 7 bits left,
Sure.
and we could store a number up to 128. So wouldn't that like provide us a
You're
few
still
more
going to lose, you've still got the issue of, the only reason we can't do,
I see.
you've still got the issue of you can't make them all ones and zeros, but yeah. And one of the reasons we don't make this number 2's complement is because comparing 2's complement numbers is kind of a nightmare. You can only say positive or negative, it's not as easy to do it. This makes it much easier. Good question. Okay, let's come back from our break. Here's a question for you. When is a floating point value an integer? Like, remember how we said that the numbers can be, we have this fraction in here and we have the exponent, but when is it actually an integer? Yeah.
If the last bit of the exponent is 1 and all the fraction is 0.
If the last bit of the exponent is 1, does that matter?
Because wouldn't it be like
If it's
2 to the 1 times the implied
Yeah.
like leading one?
Yes, but it's a little more subtle than that. You can actually get numbers that are, integers Because if you have a big exponent, and you only have a couple numbers in the significand, you're going to shift them over by enough to make it into an integer. Okay, so let's do a conversion the other way around this time. Let's convert 1, 2, 3, 4, 5, 6, 7 into floating point. Okay, now we're going to actually use 1, 2, 3, 4, 5, 7 in a floating point. Here's how you do that. Okay, you need to divide by a power of 2 so you get a number between 1 and 2. Isn't that what we said we have to get in our fraction, a number between 1 and 2? So you have to divide by a power of 2 such that you do that. Okay? So what you can do is let's first convert 1, 2, 3, 4, 5, 6, 7 to binary. Okay. So there, that's our binary there. Okay? You can go and do the conversion if you want to. That's what 127 in binary is there. Okay. Remember how we said we get that leading one for free? Just get rid of it. That is now our binary significand with extra zeros if we don't have to 23. And this, by the way, answers the question, what's an integer? If you have numbers that go beyond that, or it's not, well, it still could be an integer, but it might not be a representable integer. But anyway, you get rid of the 1 and you put that in there. And then you remove the leading one and then add 0. So this is our significand here. Okay? We actually have a few zeros at the end there. Okay? How much do we need to shift this number to get the form of 1.xxxx? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. If you take this number and you shift it by 20 to the left, you get a number between 1 and 2. That's the way it does it, right? So that means that our exponent is going to be 20. We have to add 127 because we've got that silly bias thing in there. So our number here is going to be 147. And then what's the sign going to be? Positive, so it's going to be 0. We've converted 1, 2, 3, 4, 5, 7 to binary. This is what it looks like. Now, remember what does that actually mean? This number, minus 127, 2 to that number, times 1.000 gives us back our integer. Okay? So, whoops. So, in the sense that y is it an integer in this case, if the exponent is big enough to make all these ones shift out, then it becomes an integer in that case. Does that make sense? All right. Not too critical that you know that. Now, the question during the little break came up. One of them was, hey, how do you get numbers that are like 0? Well, if we have all zeros in the exponent, okay, then what you can do is that's actually a different form. And you have to do a totally different algorithm. It's not totally different, but it's mostly different. Okay? You now have the exponent, which is 1 minus the bias. In other words, it's a really small exponent, right? Okay? And you now have the fraction without the leading 1. Why they're doing this? Just because they want to eke out as much extra data as they can, or extra ability to do these numbers as possible. And it also helps in getting really small numbers to make sure you have the right range. It's not critical that you understand that. But we now have a way to represent zeros, right? All zeros in this number is 0, right? Because this is now 2 to the negative 126th, right? But times 0 gives you 0. So all zeros is just 0. Isn't that nice that a floating point number, if we have all zeros, it means 0? That's a nice little side benefit, right? Yeah.
If you have this different algorithm for when it's all zeros, how do you get the numbers 1 through 2 then?
What's that? How do you what?
How do you get the?
How do you get if you in the previous one? 1 times 2 to the 0.
Oh yeah.
Right. 1 point whatever times 2 to the 0. Good question. What if we have a 1 in the sign bit in all zeros? It's not. It's negative 0 as it turns out. So in mathematics, sometimes you talk about negative and positive 0, especially when you're talking asymptotes coming up to the 0 line. You might say which direction is coming. That's helpful there. But it's a little quirk of this because it just happens to be negative and positive 0. You just have to know that, right? there's this thing called gradual underflow. That's the part that's extra technical that they thought about to make it like underflow nicely when you get to numbers that are really, really, really small. Go look it up if you want the details on that. That's a different form. So now we've covered numbers that are not all ones and all zeros. We've got the ones that are all zeros. What if the exponent is all ones? This is called exceptional numbers. This is numbers like 0, 1, 1, 1, 1, 1, 1, and then all zeros is positive infinity. Is it really positive infinity? No, but that's what we're going to call it. 1 with all ones is negative infinity. That's nice that we can represent that in here. Most of the other numbers are these numbers called NaN, not a number. If you divide 0 by 0, what are you going to get? It's not 0, it's not infinity, it's not a number. There are actually millions of those that are, it's actually, well, that many of them that you can actually represent as negative or as these exceptional numbers. They wanted to have a way to say, I've done a calculation and it didn't come out right. Or they wanted to say, I've done a calculation and it's infinity. And that's how they did it. They just used one extra bit in the exponent, and that's the way it goes. That's what they ended up deciding. Okay? Square root of a negative number gives you not a number. Okay? You can check those out if you want. Okay? All right, now let's talk about arithmetic. What do you think is going to happen in this program? Let's look at this program together. I'll make it a little bit bigger on the screen. Okay? All right. I'm going to have a floating point number A, 3.14. I'm going to have another floating point number 1e to the 20th. That means 1 times 10 to the 20th, by the way. You can do that and see it lets you do that. That means 1 times 10 to the 20th. Okay. I'm going to calculate two other numbers. C, which is going to be A plus B minus B. A plus B, the quantity, minus B. And I'm going to do D, which is going to be A plus the quantity B minus B. Okay? What should C and D both be? Mathematically speaking. A plus B minus B. A, right? Should be 3.14. Or A plus B minus B should also be 3.14. Right? If you run this program, okay, let's do it. This is a floating point test. Let's see. Cursor, there we go. Oops, let's see, addition. Make, install. If you run this program, you get, let's do it up here. You get, there we go. Oh, I did the wrong one. Hold on. Well, I'll just show you up here because it's one of these ones. You end up getting, in the first case, A plus B, the quantity, minus B, you end up with 0. In the second case, you do end up with what you think you should have ended up with. Now, question is why? Right? What's going on? Why is our math broken? That's the big question. Any ideas? Huh?
Some sort of like overflow of the space keys, or
Yeah, this is actually a good point. There's some sort of overflow situation going on here. Okay, something like that. It's like something's happening where you're doing that. Now, what can you tell me about 3.14 versus 1 times 10 to the 20th?
Very, very small.
Very small compared to a very big number, right? That means we should talk about arithmetic. Okay? It's a little bit more than overflowing, even though that's a good idea here. Okay? Let's look at how we represent the binaries of these. Okay? This is 3.14. Why is it 3.14? Well, this is 128 minus 1 is 127. So it's 2 to the 1 in this case. And this is 1.1001, blah, 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 right? So if you multiply that, I have to do 3.14. This is a really big number, it's basically the same as 10 to the 20th, right? It's a really big exponent on here. And this is another, just the significant parts. The difference in exponents is where you've got the problem. If you're going to add two numbers together, how do you do it? Like, in other words, if I say, let's say, if I say 1, 2, 3, 4, 5, 6.78 plus 0.000929. How do I add those together? How would you do it on paper? You'd align the decimal places, right? Which means that I could do it like this. I could go 0.0000929 and add these up like that, right? You have to align the decimal place and then start adding things. Where's the decimal place going to be on 3.14 and 1 times 10 to the 20th? Way apart from each other, right? 1 times 10 to the 20th has 20 zeros and then a decimal place. 3.14 has a decimal place right there. Okay? So, you would have to do this, right? This is what it looks like here, like this. You'd line it up. You end up, when you add those two numbers together, with a number that's like this: 1 times 10 to the 20th, 314, right? Like that's what happens when you add them. If we try to put this number into binary format, we can do that. But watch what happens. Right? You have to go do it. You have to do that whole conversion thing we kind of talked about. First, you take this number and you convert it to binary. Then you take the number itself, and you can only go down 23 bits, as it turns out. So we're going to leave off a bunch at the end there, right? And then you round up, and there's some rounding that I didn't really talk about. But then you have to see how many bits left you shift. Remember we did that earlier? Well, how do you do that from here? 1, 2, 3, 4, 5, all the way back up to this 1. Right? And it turns out that we have to shift 66 times. 66 times means that we're going to have a number 66 times away. Guess what? The number that we're cutting off here, the 3.14 is like down here somewhere. It's way down there instead of way up there. The 3.14 just disappears. It turns out that this is what we're left with. We're left with this representation, and guess what? 1 times 10 to the 20th, those are exactly the same. Those two numbers are the same. The 3.14 stuff is happening way over here. If you could represent it, you can't because we only have a fixed number of bits. So arithmetic breaks when you do numbers that are really big and try to add them to numbers that are really small, proportionally. Arithmetic breaks, right? We say that floating point arithmetic is not associative. In other words, you can't put those parentheses around and say that this and this, mathematically they're the same, not in floating point notation. You have to be careful about that. If you ever find yourself in a position where you're doing something with two numbers that are vastly different, be careful, because they might end up dropping things out that you don't want. Okay, so that's an interesting side effect. Here's another example. Take a look at this example. Okay, 0.1, 0.2, 0.3. I'm calculating D is A plus B, 0.1 plus 0.2, right? And then I'm doing this printf in here that says, do you guys know this form of printf, or I'm sorry, this form of an if statement? Basically it says, if this is true, do this thing. If this is false, do this thing. Well, the question is, I'm saying, is A plus B equal to C? Is A plus B, which is 0.3, mathematically, equal to 0.3 here? What do you think? Yeah, I wouldn't ask this if it was the case, right? It turns out it's false, right? The rounding that happens when you do 0.1 plus 0.2 doesn't produce the same number as just saying 0.3. Why? Because you can't. Because that's the way the floating point numbers work out. You can expand this a little bit and show. And there's another program you can run where it's going to show what 0.1 is and 0.2 is. 0.1 is 0.100, and remember there's other zeros at the end of it. There's other stuff at the end of that. And 0.2 is this, right? 0.3 is this. Point A plus B, there's some craziness happening down here when you're trying to add those together. That 0.3 is not the same as A plus B. Turns out it just doesn't work. So you have to be careful there too. Careful that one. Here's another example. All right, this one should be a dead easy one to mathematically, this is what's going on. All I'm going to say, ask is 167772224.0 equal to 1.167772225.0. Well, are they equal? No, of Of course they're not. When you run the program, it says they're equal. Why? Why would this program tell me that 167772224 is equal to 1677225? Bits got lost. If you try to represent 1677224, actually let's do this. We can do this on the, over here. We can do it on this one. Not this one, but, nope, hang on. Oh, where'd it go? Hang on, floating point converter. I think it's the first one that normally comes up. There it is. Okay. All right, ready? 16777, what was it? 224. 224 looks like this. Let me make it a little smaller here. Looks like this. It's got an exponent of 151 minus 27. 151 minus 27 gives you 124. Okay, 2 to the 124. Sorry, I lied. 151 minus 127 should give you 24, right? 24. 2 to the 24th. And look where that little 1 is over there. Right? Way down there. Okay? In fact, I'll make it like that. Okay. And if we try to do 1677225, guess what? It's the same exact bit pattern. Because of the fact that when you're doing the conversion, you lose bits on the end that you're not going to be able to deal with. The difference between this number 224 versus 225 would be these bits over here. Does that mean there are some floating point numbers that are integers that you can't represent? Sure there are. There are millions of them, right? Why? Because they just happen to fall off the end like this. And so what it means is that you've got to be very, very careful. So if you were to write a program that compared 162224 to 167772225 in a for loop or something and stopped when it got bigger than that, you might write a program that loops forever. Even though logically you'd think, mathematically, it would work just fine. Here's the thing. You should not compare floating point numbers. Very difficult to compare floating point numbers because of this sort of issue. Two numbers might be the same or might be different. Just, you won't necessarily know unless you know enough about the underlying thing. Okay? So it's a little crazy that you could do that. Yes, question, Julia. Mm-hmm.
First one is, so is the reason why we use doubles a lot just because it's much larger capacity, so we likely won't run into the issue, but we would run into the same issues if we got to numbers that are big enough?
Yes, so the question was, look, and you're kind of asking me between the difference of floats and doubles, let's say. Yeah, so floats, if you just type float A, it means that it's a floating, it's a 32-bit. If you type double, it's 64-bit. So yes, if you use doubles, you will get a much higher range before you run into the problem with this. Now you could figure out, if you did a little calculations, you could figure out what the first integer, this happens to be the first integer that doesn't work. Like you can't represent 167772225 exactly in 32-bit floating point format because the bits drop off the end and it becomes the same pattern as this one. That's the problem. There's one in the double. It's just much, much bigger. So yeah, so you get most of the range, or you get a lot more integers before you run into this problem. Yeah, good question, Lisa.
So 2 to something huge, I don't know what it is, like 16,777,216. So is everything smaller than that? Would that work? Like if you were to compare like 2 ones or like 16 million blah 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 216 is equal to 16 million blah 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 215. Would that?
It depends. So it depends which ones you're looking at, as it turns out. The way, if you went and converted these two, it turns out they're the same format. 167772226 happens to have a different one than these two. So some of the numbers just happen to be missing. Some of the integers happen to be missing. But remember, we're not talking about integers. Like, are these integers? No, they're floating point numbers. Now, in math terms, they happen to be integers, but the way we've represented them, you can't represent this one differently than this one. It just won't work out. But yeah, so after you get past these numbers, the problem is it's because of the 2 to the, in this case, 24th or whatever, there's only 23 digits of precision, right? Once you get to the 24th, you gotta lose some digits at the end. That's just what's gonna happen. Very good question. Yeah.
I think another part of your question, I don't know if I'm like understanding correctly, but was also that like the 216, 215 example would all integers before this always work?
Yes, all the integers before this happen to work. Yeah, and it's partially because you're only getting 2 to the 22 or less, which you can always, you'll never shift enough bits out to make them different. This time, this is the first case where you shift too many bits out, oh, it's different. That's the end answer. Yeah.
I had another question.
Yeah.
So throughout the PowerPoint we've been saying like, or the presentation, we've been saying shift left however many necessary.
Yes.
But I'm kind of confused because I understand it's like shifting the decimal.
Shifting the decimal place or the binary place, not shifting the number.
Right.
You're right shifting the number.
Okay.
Yes, I'm just thinking about how, maybe I should phrase that differently. Yes, it's how many places do you have to move the decimal to the left, or the binary point to the left. Yeah. Good questions. Anybody else have questions? People thinking about like, this is it's a cool format, and it happens to be how all the numbers are done on all your computers these days. Yeah.
So what does the algorithm for building the mantissa look like?
What does the algorithm for building the mantissa look like?
It can't be too simple, eh?
Well, it's not bad. I mean, it's this one right here, right? You take, if you're converting from a decimal, let's say, right? First, you take that decimal, you convert it to a binary number, which may have an infinite number of digits. You chop it off after 23, and that's the mantissa, except for that leading one goes away because we don't need it. But we know it's there, so we don't represent it. That's how you end up doing it. But there's some other nuances. Now, other nuances, the hardware handles most of this, by the way. And the hardware itself is the one that's saying, oh, is it denormalized, is it exponent, or is it an exceptional number, etc. So it's not a fast process necessarily, although they try to make it as fast and as efficient as possible. And they've eked out every last bit you can. Yeah. Oh, and by the way, there's one other interesting thing. Sometimes in the underlying hardware, they actually have a couple extra bits there that they leave in there so that you can do rounding nicely, turns out. But you don't need to, that's not part of the format. Other questions about this stuff? Numbers are interesting. Here are the takeaways here. This was a carefully thought out thing. It's not like I'm just standing up here doing something that was somebody just determined or just came up with one day and like discovered. This was not a discovery, this was a plan. Right? It's not simple. You'll notice it's not simple. There's a lot of things swimming around like, oh, you got to add 127 and do this, and it's 2 to the whatever. It's not simple, but good engineering design. Okay? Floating point numbers represent a huge range, right? Remember, a 32-bit float can only hold 4 billion different numbers because 2 to the 32 is 4 billion plus some, right? You only have 4 billion numbers there, but the range that you can have goes from negative 3.4 times 10 to the third negative 38, or 10 to the 38, to positive 3.4 times 10 to the 38, right? That is a huge range. Not to mention the fact that you've also got the tiniest numbers too. I mean, there's a range from 10 to the negative, or 10 to the 38, negative 10 to 38, to 10 times 10 to the 38. It's a lot, but there's a lot of numbers missing in there, right? You can't get exact representations of that many numbers because you've got this huge range. Doubles are a huge, even bigger range. 1.7 times 10 to the 308. That's a huge, huge number. Like, there aren't many things in the universe that you need to use numbers like 308, 10 to the 308 for, right? They represent real things. Certainly mathematically you can do that, but that's that, right? There are many integers are missing, right? A trillion in 32-point format, you cannot represent exactly. You can't do it. It's the same exact issue as that other number I showed you earlier, right? You almost never want to use floats for currency because of these sorts of things. You'll have rounding errors, you'll have comparison errors, and you just don't want to compare. Okay? So that's the way numbers are built that are not integers on your computer. Julia.
So the only reason we can use doubles for currency is because we don't have that much money.
I mean, you still won't use doubles for currency. If you're a bank, you're not going to use doubles in your program. You're going to use a library that's called like, big number or something that actually will represent exactly, or you'll use some sort of fixed point format. Fixed point is kind of nice because you can add a couple extra and you know that you've got that. But yeah, I mean, you still don't want to use doubles. I mean, the problem with doubles, again, there are still lots of numbers you can't compare to exactly. 0.1 plus 0.2 doesn't necessarily equal 0.3, even though you mathematically think it does. So you have to still be careful with even with doubles. Yeah. But you should almost always prefer doubles over floats unless you really care about speed, because doubles will be much slower. Other questions on this stuff? Okay, hopefully that was kind of interesting to you. Okay, you have to also associativity, numbers are not exact, equality, don't do comparisons. And many times GCC will actually warn you if you try to compare two floating numbers. It'll go, are you sure you want to do that? That's not necessarily safe, so it'll tell you that. Lots of other stuff you want to read about this and dig into it. All right. See you guys on Monday for the last lecture.